Hello everyone. In this video, I am talking about gas mixture. So basically, I am starting chapter 13 in our textbook. So far in the discussions that we had in our course, we were discussing about a single pure substance. So basically, I would say so far we discussed about properties of a single, or let's say properties of single pure substance. So for example, we were just dealing with one substance, for instance, water only or hydrogen only. But what if we are dealing with a mixture of several pure substances, and that has lots of application in thermodynamics. So in this chapter, we will discuss about systems with several pure substances. Basically, we are discussing about gas mixture. What if we have different substances in one particular system? What if those substances are mixed with each other? So the properties of a gas mixture basically depends on the properties of each gas or each individual gases. So the properties of a gas mixture depends on, so this is depends on the properties of the individual gases. Okay, so those individual gases are called components. Okay, called components. Also, the amount of each gas defines the properties of the gas mixture. Also, the amount of each component defines the properties of the mixture. Okay, now the composition of a gas mixture can be described in two different ways. In one approach, we are looking at the number of moles. So this is molar analysis. In the other approach, we are looking at the mass of each component. So let me say the composition of gas mixtures can be described in two ways or in two methods, let's say. Number one, based on the molar mass, or let's say specifying the number of moles of each component. All right, so this is basically the molar analysis. And in the second approach, number two, we are specifying the mass of each component. and this is gravimetric analysis. Okay, so in a mixture with k number of components, I can write the mass of mixture based on this. So let's say in a mixture of k components, I can say that the mass of mixture showing with m, lowercase m standing for mass, and this is standing for mixture. Mass of mixture is sum of mass of each component. So let's say we have k number of components. So mm is sum of mi, and I starts from 1 to k. Okay, so this is mass of mixture. For example, it can be in kilogram, and mi is mass of each component, again in kilogram. Okay, also the number of moles in a mixture is equal to the sum of the number of moles of each component. So n m is equal to the sum of n I, and I starting from 1 to k. So nm is going to be mole number of mixture, mole number of mixture, and ni is mole number of each component, mole number of each component. Okay, the other definition that we have is mass fraction. So mass fraction is the ratio of mass of a component to the total mass of the mixture. So mass fraction is the ratio of mass of a component to the mass of the mixture. So we show mass fraction with mf subscript I. So this is mass fraction for component I is equal to the mass of component I to mass of mixture. Okay, so obviously it's a dimensionless number because this is mass divided by mass. The other definition that we have is mole fraction. So the concept is pretty much the same, but instead of m, we have the number of moles. So mole fraction, which we show with y, mole fraction is the ratio of the mole number of a component to the mole number of the mixture. So we show that with y subscript I, this is the mole fraction, is equal to the mole of one component, and capital N is the number of moles, and Nm is the number of moles in the mixture. So obviously, some of these MFI and capital N is equal to 1. So sigma MFI is equal to 1 and sigma YI is equal to 1. And I starting from 1 to k. K is the number of components that we have, and likewise sigma yi is equal to 1, and again I starts from 1 to k number of components. Okay, the other definition that we have is called the apparent molar mass. So we show that with capital M subscript m, which is called the apparent molar mass, which is equal to the mass of mixture over number of mole in the mixture. So this mm is apparent molar mass. And unit wise, we'll discuss about that later, but the unit will be kilogram per number of moles. Let's say kilogram per kilomole, for instance. So instead of I can say sigma mi, and instead of I can just write it as nm for now. But one thing I can do, I can expand this I can write it as number of moles in each component multiplied by the molar mass of each component. So both of them are just for one component, but that I starts from 1 to k obviously. And here in the denominator, I still keep nm. So the denominator is the number of moles we have in the mixture. This is the number of mole in one particular component multiplied by molar mass of that component. So Ni over Nm, we had a definition for that, and that is called the mole fraction, or Yi. So I can rewrite this by Yi. So this will be equal to sigma yi mi. Okay, and I starts from 1 to k. So this mi is molar mass of each component. Okay. And mm is, as I said, is called apparent molar mass. The other thing that we can define for the mixture is Rm. Okay, and Rm is gas constant of the mixture. So that Rm is Ru, which is the universal gas constant, or that 8.314 kilojoule per kilogram Kelvin, divided by molar mass of the mixture. So this Rm is gas constant of mixture. Ru is the universal gas constant, which is 8.314 kilojoule per kilomole Kelvin. And mm is, as we had before, is the number of moles within the mixture. All right, so the other definition that we have is, I need to correct this mm. So this mm is molar mass of the mixture. I was trying to look to find it in my notes. It's right here. So mm is the molar mass of the mixture. I think I mentioned its number of moles. This is not the number of moles. This is apparent molar mass. Okay. So the other definition that we have basically correlates mass with the ratio of the molar mass. So let's say if I start with MFI, which is mass fraction, so that mass fraction is MI over MM. And once again, MI is mass of component I, and MM is the mass of mixture. Now I can write this mass of component based on the number of moles multiplied by the molar mass. Okay, so N in general is number of moles, M is molar mass. Okay, so let's say the unit is, let's say kilomole, for instance. Usually we are using kilomole. molar mass is kilogram per kilomole. These are the units basically. And lowercase m is mass, kilogram. Well, we may use gram instead of kilogram and etc. So mass of mixture is written by the number of moles in the mixture multiplied by molar mass of the mixture, and that is equal to yi, and yi is the mole fraction multiplied by mi over mm. If you're wondering where this yi comes from, this is basically ni over nm. So that is pretty much it. Now, I think at this time we can do a couple of problems, or at least one sample problem, and after that we can continue our discussion.